Hello everyone, this is Ritam Majumdar. Today I will be presenting our paper, How Important are Specialized Transforms in Neural Operators. Various transform-based neural operators like Fourier neural operators, wavelet neural operators, Laplace neural operators have been popular for obtaining solutions for parameterized PDEs. Different kinds of specialized transforms like Fourier, wavelet, Laplace perform better over the others over a specific PDE problem in hand. However, as all these transforms are linear in nature, we seek to investigate that whether using a parameterized linear transform can perform better than a specialized transform and generalize to the governing PD problem, hence re-evaluating and re-investigating the need for specialized transforms. We define our problem statement. We seek to learn an operator mapping input function spaces like changing initial conditions, boundary conditions, parameterized PDE coefficients, etc. to output function spaces like solutions of parameterized PDEs. We first look at the architecture of Fourier neural operator. Here Fn and F inverse n refer to the Fourier and the inverse n-dimensional Fourier transform. P refers to the projection of the signal from lower dimension space to higher dimension space. R refers to the linear tensor multiplication. Sigma refers to the nonlinear activations, and Q projects the higher dimensional signal back to our projection in the output space. In this paper, we modify the transform block of the neural operator represented in the ochre yellow block by replacing the one-dimensional Fourier transform or wavelet transform by a learnable transform, which is essentially a matrix multiplication. Uh, what are the differences between 1D FNOs and our work? It is we replace F with a linear transform M and F inverse with another linear transform N. Since Fourier transforms map the signal in complex space, the tensor R is complex in nature, the parameter R is complex in nature, whereas in our case, the tensor R is linear real in nature. Additionally, M and N aren't inverse operations of one another, unlike in FNOs or WNOs. We scale things up to n-dimensional neural operators and investigate the differences between an n-dimensional FNO and our n-dimensional operator. It is known that an n-dimensional Fourier transform is equivalent to taking n one-dimensional Fourier transforms over each dimension. Equivalent to FNOs, we extend our neural operator by taking n linear transformations over every dimension and don't share the weights of the linear transform across dimensions so as to keep the operations separate. This is one key difference between FNOs or WNOs and our architectures. Our operators aren't same across dimensions, nor are our operators inverses of one another, MNN, unlike FNOs or WNOs. To summarize, we replace the non-parameterized Fourier wavelet transform F or W and its inverses with a parameterized linear transforms M and N, and R is a real tensor as against FNOs and WNOs, where R is a complex tensor which is parameterized. For consistent benchmarking, we consider the same set of PDE problems considered by Lee et al. In Fourier neural operators and Tripura et al. In wavelet neural operators, along with the hyperparameters under consideration. We discuss the results. We observe across all examples that neural operators perform competitively against FNOs and WNOs, outperforms WNOs everywhere, even on high-dimensional partial differential equations like Navier-Stokes and turbulent Kolmogorov flows. Our parameterized linear transforms also generalize to examples like one-dimensional wave advection equation and uh, triangular Darcy notch, where Fourier neural operators fail to generalize. We also observe linear transforms converge faster than FNOs and WNOs. We investigate the reason behind this and evaluate the total number of parameters of our neural architecture. Despite having additional parameters due to taking learnable transforms, There is an overall parameter reduction due to our tensor R being in the real space as against FNOs and WNOs where R is in the complex space. We take every complex space has twice the number of parameters as a real parameter, and since we have lower number of parameters in our neural operators, we converge tend to. We make our code and datasets available in the following link. Please feel free to check the paper and code out. Thank you very much.